Okay, we're here to do an example of a collision, and I'm going to use a method for collision analysis that I really think that you should use. I'm going to ask a question about center of mass velocity, and um, it's basically using the techniques that I'll be demonstrating here and the techniques that I discussed in the notes. So here's the setup. Um, let's say 5 kilogram heavy ball is thrown with a speed of 7 meters per second, which I think is fairly fast for such a heavy ball. Um, eh, let's make it 10 meters per second. That's really fast. When the ball gets to a 60 kilogram um, person who can catch the ball or bounce off elastically. And I want to know what happens to the person in each case. So either of these is considered a collision, and in any collision, um, I want to be thinking about conservation of momentum. So um, so we want to know if we can find the total momentum. And in this case, we do have enough information about the initial conditions to find the total momentum. So the P total is equal to M1, let's label this initial. P total is M1 V1 plus M2 V2. So this would be the 5 kilograms times 10 meters per second plus 0 for the person who I'm going to assume the person is initially at rest. And that gives me a value of 50 kilogram meters per second for the total momentum. Now the next thing we need to do is we need the velocity of the center of mass. And here is how that is defined. The total momentum is equal to the total mass times the velocity of the center of mass. So you see that that is a momentum formula very similar to our initial total momentum formula, except in this version, instead of thinking about these as two separate objects, M1 and M2, I think about them as one total object. So then I can plug numbers in because I calculated the total momentum to be 50. I know the mass total is 65 times V center of mass. So then V center of mass is equal to 50 over 65. And I kind of want to just bring up a little spreadsheet calculator off of my other monitor here. So M1 is 5, V1 initial is 10, M2 is 60, V2 initial is 0, and P total is equal to M1 V1 plus M2 V2. So V, center of mass, is equal to the total momentum, which is 50, divided by the total mass, which is 65. Sorry about that little delay there. And this comes out to 0.7, whoops, 0.769 meters per second. So even though the ball is moving 10 meters per second and the person is standing still, the net result is there's a center of mass somewhere in between them, kind of an average location for the two objects, and that center of mass is moving at just under a meter per second. Now, in the first case, if the person catches the object, this is something called a perfectly inelastic collision. And in that case, both objects have the same velocity. Since V, center of mass, is an average-ish or an average velocity of the objects, it's a weighted average velocity of the objects, then this is now their velocity. So if caught, then V1 final is equal to 0.769 meters per second, and V2 final is also equal to 0.769 meters per second. And this was the middle step in the pendulum lab that you are looking at sometime this week, the ballistic pendulum lab. Now, I want to show you how to deal with the elastic collision. And for that, we need to do more calculations. So, initial, we have the ball, 5 kilograms, and it is moving this way with 10 meters per second. And we have the person with, what was it? 60 kilograms? 60 kilograms. And what we learned so far is there's a center of mass that's somewhere in between them. It's actually about right here. So this is the center of mass, and it's moving very slowly in that direction. It's moving with a speed of 0.769 meters per second. So here's what we calculate. V1 prime is V1 minus V center of mass. A relative velocity is calculated as a subtraction of two velocities. So this is 10 minus 0.769 is equal to V initial prime is equal to V1 minus V center of mass, 9.231. 9.23 per second. And And this is how fast M1 is approaching the center of mass. So initially, they're maybe 9 meters away from the center of mass, and 1 second later, they are at the center of mass. They only have to catch up a shorter distance than they have to travel to get to the actual other mass. Then we also calculate V2 prime is V2 minus V center of mass. This one might look a little weird because V2 was 0. And then we're still subtracting the 0.769, and we get negative 0.769 second. And what that's saying is that M2 is actually getting closer to the center of mass. Now, that's easiest to see if we look at what the final condition looks like. The final condition looks like M1 and the center of mass and M2 are all together at the same place. So saying that V2 prime is negative before the collision is basically saying that the 60 kilogram mass is, you can think of the blue dot as moving toward the 60 kilogram mass, or you can think of the 60 kilogram mass as moving backwards toward the blue dot. And that's why this is negative, because from the perspective of the center of mass, M2 has moved backwards a little bit towards the center of mass. So either way, we calculate a primed velocity relative to the center of mass by taking the original velocity and subtracting the center of mass velocity. And here is where the magic happens. Actually, this isn't the final state. This is the impact. We're not actually going to calculate velocities at that point of impact. We're going to go after it and look at what things look like after the collision. In an elastic collision, the velocities relative to the center of mass, which are the ones called V1 prime and V2 prime. They simply reverse. So now we draw another line, at least that's how I do it. I draw another line across the page. And I think about final conditions. And we're going to have M2 is going to get bumped in that direction. V2 final, I guess, but it's V2. M1 is going to bounce off M1 and be moving in that direction, V1 final. And the center of mass is going to be in here like this, center of mass. So here's what we know about the two velocities. The new V1 prime is now negative 9.231 per second. It's the same magnitude as it was before, just in the opposite direction. V2 prime is now plus 0.769 per second. It's the same magnitude as it was, but now it's the opposite direction. It's plus instead of minus. And there's one more, V center of mass. Doesn't change. So V center of mass is still equal to the regular old value 0.769 meters per second. The same value that we calculated up here. Right there, that value right there, 0.769 meters per second. So now we can reconstruct V1 prime equals V1 minus V center of mass. That's our definition equation for how to calculate the primed velocity, is we take the unprimed velocity and subtract the center of mass. So now we're after the collision. Instead of knowing V1, we know V1 prime. So this is minus 9.231 equals V1 minus 0.769. So I plug in my negative velocity now on the left. I don't know V1 yet, but I do know V center of mass because it never changed. I plug that in, and now I see I can just add 0.769 to both sides. And I'm going over here to my spreadsheet, calculate it. Oops. V1 final is so this is negative 9.231 plus 0.769. And that comes out to negative 8.462. So that's this thing. So the ball bounces off the person and comes back with 8.462 meters per second of velocity. Now, initially, it had 10 meters per second. Now it's not moving so fast. So it doesn't have as much energy as it used to have. We can do the same thing for V2. V2 prime is equal to V2 minus V center of mass. That's how we calculate a relative velocity. Then how do we figure out V2? Well, we just take V2 prime plus V center of mass. So we have 0.769 plus 0.769 is equal to V2 final prime equal to, oops, that plus that. Now that I've done it in a spreadsheet, I have for myself an elastic collision calculator that I can use to help answer homework questions and help figure out how to help you guys in more of a tutoring situation. 1.58 meters per second. So that's this one. So now we know what happens to the person when the ball bounces off of them. Notice that if they catch the ball, they only gain just under 1 meter per second of velocity. If the ball bounces off them, then they gain 1.538 meters per second of velocity. Now there is an important collision quantity that I want to calculate that um, is called the impulse of the collision. And that is delta P, 1 magnitude, or magnitude of delta P2. the change in momentum of an object is an impulse. It could be the combination of many impulses, or if there's only one force causing it, then it's just a single impulse. So we can calculate P1 initial, which was 50 kilogram meter per second, and P1 final is the mass, which was 5 kilograms, times the velocity, which is negative 8.462, and E1 final is M1 times V1 final, negative 42.3. So delta P1 is equal to P1 final minus P1 initial is negative 42.3 minus 50 equals minus 92.3 kilogram meters per second. So the magnitude of delta P1 is equal to 92.3 kilogram meters per second. That's a measure of how violent the collision is. The more impulse, the more violent the collision is. If we had calculated delta P2, delta P2 is P2 final minus P2 initial. P2 final is the mass times the final velocity, which is 1.538, minus 0, because the initial velocity was 0, so the initial momentum is 0. This is also going to come out to 92.3 kilogram meters per second. Note that these two values are opposite to each other. And that's because the momentum that was taken away from the ball, the 92.3 kilogram meters per second was taken away from the ball, is given to the person in that collision. And one more thing we have to calculate. We say that an elastic collision conserves kinetic energy, and I want to find out if we actually did this. So let's calculate K initial is just 1/2 M1 V1 initial squared, and that is 1/2 times 5 kilograms times 10 meters per second quantity squared is 2.5 times 100 is 250 joules. Final, K1 final is 1/2 times 5 times, what's its velocity? 8.462 quantity squared. I don't care about the negative sign because um, I'm squaring it anyway. So K1 final is 1/2 times M1 times V1 final squared. If I'm doing it in Excel, I don't need to worry about the minus sign. It just gets canceled by itself. If you're doing it in a calculator, you got to be careful about that minus sign because you don't want to accidentally make part of your equation negative if it's squared and it's supposed to come out positive because it's squared. This is 179 joules. K2 final is 1/2 times 60 times 1.538 squared. So 1/2 times M2 times V2 final squared is 71 joules. And notice K final total is the total of those 250 joules. Check. We have confirmed that the calculations we did produce results that have conservation of energy. So that's a nice big example with lots of numbers, but the numbers fit together very nicely, showing all the important things we have to calculate about a collision. We have to be able to calculate the final velocity. We want to be able to check on conservation of energy during a collision. And very often we're concerned about the impulse of a collision, which is the momentum change of either object.